Good afternoon, everyone. What we're looking at today is we're actually moving from first principles into the actual shortcut rule, which I think will make a lot of people happy and a lot of people mad at me that I made you go through first principles in the first place. So prove that if f of x is x squared plus 2x plus 1, that f dash x is 2x plus 2. Now, we've done this question before through first principles, and this is in fact the correct answer. But what I want to do is I want to show you it on your CAS. All right, so here it is. And on your CAS, under keyboard, I want you to go to Math 2, and then I want you to find the third row, second column button, and it looks like this. And then what I want you to do is in the bottom one, I want you to put an X in there, and then I want you to type x squared plus 2x plus 1, and it spits out the answer for you. All right, so this is using your CAS to do differentiation, and it does differentiation using the shortcut. All right, asking it to do it first principles, not really going to work. All right, sometimes it does, but usually not. So ddx is what we use for the most part. All right, so what do you notice on the, what do you notice about how the equation is written? Well, comparing the two equations. So if I look here, compare the two equations, f of x and f dash x. Compare the powers. What are the orders? What are the orders that these equations are to each other? What sort of equation is that? What sort of equation is that? So compare this equation. What sort of equation is it? It's a quadratic. And what is its derivative equation? It's a linear. All right. So if I write, okay, well, if f of x is x cubed, f dash x is going to be 3x squared. So f of x, what's this? Cubic? And its derivative, what is its derivative? All right. Look at its derivative. So the original is a cubic, but what's its derivative now? It's only a quadratic. So every time I take the derivative of something, what is happening to the order of that function? What's happening each time? It's decreasing, but how much is it decreasing by? Yeah, it's decreasing in power by how much? By 1 each time. Yeah, that's correct. So, looking at this one here, where's that 3 gone? So there's the 3 here. Where's that 3 moved to? So if you compare where the 3 is in the f of x to where it is in f dash x, what's happened to it? Yeah, so it used to be the power, but now it's the coefficient of x squared. All right, so remember that's the coefficient. That's the coefficient that we need to be worrying about. All right. So if f dash x was 2x to the 4, f dash x is going to be 8x cubed. All right. So again, following along with the pattern, I've got 2x to the 4. I've taken the derivative of it, and now I have 8x cubed. So what's happened to the power? Yeah. And it's 2 times 4 is 8. All right. So this leads us to this. So ax to the n if f of x is ax to the power of n, then f dash x is going to be equal to anx to the power of n minus 1. Decrease the power, put the original power down the front, times it all together. All right, so this is what happens. This is what happens before. 2x to the 4, a is 2, n is 4. 4 comes down, 4 times 2 is 8, subtract 1 off the power. All right, now this process works for longer things as well. All right, so this is just a simple shortcut for a single term, but for multiple terms, the process still works. So for example, if I say, okay, well, I'm going to do f of x plus 5x squared plus 6x minus 7, I can simply go through and follow this rule. 3 goes down the front, take 1 off the power. 2 goes down the front, 5 times 2 times x, 1 off the power, so that's 2 minus 1, which is 1. Then here, 6 times 1 times x to the 1 minus 1. Yeah. All right. And then, does this 7 exist in the derivative? Is there an x in here for me to do anything with? No. So what actually happens is when you take the derivative of it, it actually just straight up disappears. So now I have 3x squared plus 10x to the 1. It's x to the 1, so do I need to write anything? Nope. So I just leave it, 10x. And then I have 6 times 1 times x to the 0. What's x to the 0? What is anything to the power of 0? It's not 0, it's 1. All right, remember that x to the 0 is equal to 1. So it's going to be 6 times 1 times x to the 0, which is 1. So it's 6. So let's turn on our CAS again. And let's do ddx x cubed plus 5x squared plus 6x minus 7 And the answer is 3x squared plus 10x plus 6. Oh, would you look at that? Magic. All right. This rule and this pattern will help you find the differential equations of practically everything, because it doesn't require first principles, which is a lot more mind intensive because you have to do all that stuff with H and limits and all sort of stuff. The rule is much, much easier. So if you remember last week on the RMIT worksheet, one of the questions asked you to find the differential, and the equation included 1 on x. All right, which, no. First principles, that's not going to be an easy thing. However, using this pattern, using our understanding of this rule, it actually becomes trivial. All right. If I were to do this equation, how can I express 1 on x using index notation, using powers? All right, how can I write 1 on x in index notation? To the power of -1, that is correct. So that is the same as x to the -1. And what that means then is, because I now have x to the power, I can do the same thing with the rule that I have been doing this entire time. I can take that, whack it down the front, and then subtract 1 from the power. So if I take -1, put it down the front, I have -1x. What -1 minus 1 is -2. That means that f dash x is equal to -1 x to the -2, which then I can turn it back. I could turn this back into a fraction by saying, well, x to the minus n is actually equal to 1 on x to the n. And that means that f dash x is actually equal to -1 over x squared. And all right, so x to the -1 is equal to 1 on x to the n. If I look at our CAS for a second, d dx, differential with respect to x, 1 on x, the answer is -1 on x squared. I think I've made my point. All right, it takes something a little bit more complicated and makes it almost trivially easy. You just have to remember the pattern. All right, now, in function notation, we write it as f dash x. Some places will ask you to do it as such things like, oh, well, it might be dy dx. So if y equals blur, then find dy dx. Other times it's going to be just fine. Just do d dx bracket blur. You know, so there's lots of different ways to do it, but it all means the same thing in the end. You're taking the differential and you're finding the differential equation. Using that differential equation is something that we're going to look at next week. But for now, what we are looking at is just practicing that pattern, practicing that skill of creating these equations. All right. All right, so what I'm going to do is I'm going to give you a couple of extra ones to do right now, and then you can move on to 17B out of the textbook. So the questions I want you to do. So this is all find dy dx. Y equals 2x cubed plus 3x squared plus 9x. Question 2, y equals x to the 4 plus 2x cubed plus 8x plus 1. And the third one is going to be y equals yes, I can move the cows, yes. All right. So 3 questions that I want you to do with dy dx. Once you have done them, I want you to send me your answer, type it out, send it to me as an answer in the private chat, and then you may leave. All right? So do these 3, send me your answers through the private chat, move on with our lives. And then you can move on to do 17B. All right?